Hello everybody. This week we will start with the concepts of expected value and standard deviation for random variables, both discrete and continuous random variables. So in this video I will be talking about expected value and standard deviation for discrete random variables. And one such example is the one that we went through last week. Consider the random variable x, which basically counts, I should say, the number of heads when you flip, when you roll, I should say, maybe when you roll 3 dice. So we know that when you roll 3 dice, the outcome will take the values of x, will take one of the following values. It will take the values of either 0 or 1 or 2 or 3, meaning when you flip a dice 3 times, or if you were to flip 3 dice simultaneously, either you will get no heads, or 1 heads, or 2 heads, or 3 heads. For instance, if you got 1 head, it means the other 2 came up tails. All right, and if you remember last week, we learned how to calculate these probabilities with the probability of 1 heads. I think the probability was 1/8. 1 head will come out with probability 3/8, and so on. 2 heads will probability 3/8, and finally 3 heads with probability 1/8 again. And we went on to draw the histogram as well. Now what I want to do is to calculate the expected value of this random variable. Now what do we mean by expected? Let me write that down. Expected value. Expected value is basically an average. It's a weighted average, and if you ask what are the weights, so this is simply a weighted average where the weights are actually the probabilities. So it's a probability weighted average. So in our case, we know the individual probabilities. Let me probably go ahead and highlight them. Oops, draw. There you go. So we know the individual probabilities for each outcome. So what we are supposed to do then is the following. With 1/8 chance, we'll get a 0. With 3/8 chance, we'll get 1. When I say 1, I mean 1 heads. With 3/8 chance, we'll get 2 heads, and so on. With 1/8 chance, we'll get 3 heads. So, and that's pretty much it. That's the drill, basically. So let's just do it. With 1/8 chance, we'll get 0 heads. With 3/8 chance, we'll get 1 head. With 3/8 chance, we'll get 2 heads. And with 1/8 chance, we'll get a single head. I meant to say 3 heads, I should say. And that's it. So the rest is just to go through the algebra. So, well, obviously this one is 0. So 3 plus 6 is 9, plus 3, 12. 12/8, which is 3/2, or 1.5. Now we can, in a similar way, calculate the variance of this random variable. Expected value is an average type of statistic. It's the average versus standard deviation, or the variance. Let's start with variance. Standard deviation is very easy once you have the variance. Standard deviation turns out to be just the square root of the variance, so it will be very straightforward. So variance or standard deviation are related to deviation, as you can imagine, the dispersion in the data, well, in our random variable. So how is it measured? There's usually 2 different ways you can do that. One of them is very straightforward, and it's the following. It is the expectation of all the squared, let me write it like this, all the squared deviations. There you go. The expected value of the squared deviations. Well, you might wonder what is mu. I should have probably mentioned it earlier here. Expected value, sometimes it is represented like this. So it's an operator, the expectation operator applied to the random variable x, but sometimes we just go ahead and represent it with the letter mu. Mu means the mean of the random variable or the distribution. All right, so basically, because in the end it's just an expectation, and we just learned how to handle expectations here, it's rather straightforward. So expectation is a weighted average where weights are probabilities, weighted average, probability weighted average of squared deviation. So the probability 1/8 chance, let's do it, let's do the drill together. 1/8 chance, the outcome will be a 0, but we know that the mean is 1.5 and we need to square it. Does that make sense? Let me just go ahead like this. I think there's an extra parenthesis there, so times plus 3/8 chance, the outcome will be 1 versus the mean is 1.5 and we square it. With 3/8 chance, the outcome is a 2 and the mean is 1.5 and we square it. And with 1/8 chance, the outcome is a 3, whereas the mean is 1.5. In all these calculations, you probably observe that the mean is always 1.5. So that part is fixed. Yeah, it's very straightforward. And that's it. The rest is just to finish the calculation. I can factor out the 1/8. So what we have here inside the first parenthesis is minus 1.5. Squared is 2.25. Let's just have it like that. Plus, we still have a 3 here. 1 minus 1.5 is minus 0.5. Squared it is 0.25. And 3 times that is 0.75. Plus, again, 2 minus 1.5 is 0.5. Square it is 0.25. And 3 times 0.75. And lastly, the last one, 1.5 squared is again 2.25. And that's it. So we can just add up these numbers. 2.25 plus 0.75 is 3. Again, 2.25 plus 0.75 is another 3. So they will add up to a 6/8, which is 3/4 or 0.75. That's it. That's our variance. Now, standard deviation, as a result, I mentioned it just a few minutes ago, that it is just the square root of the variance. So the square root of that number, 0.75, and if you use a calculator, I believe this comes out as 0.866. Very, very straightforward. Earlier I was mentioning that there's an alternative way to calculate the variance, which turns out to make life a little bit easier. So I would like to provide that formula as well, I guess, right? So, and it is the following. It's actually based on the properties of like expanding this expression. If you want, let me just do it over here. So we're going to provide an alternative formula for that one. So variance is equal to the expectation of, let me just go ahead and square it. So we have an x squared minus 2x mu plus mu square. You don't have to learn this proof if you don't want to. The end result is the important thing, but in case you forget the formula, you can derive it, and I'm just doing it. Because expectation is a linear operator, what it means is it can distribute. So we can distribute the expectation operator here, ex squared minus e of 2x mu plus e of, oops, sorry for that, mu square. There you go. And now what we can do is, let's put an equal sign here again. Ex squared, there's pretty much nothing we can do about that one. So that one stays. All right, so the 2 here and the mu, they are just numbers. And it turns out numbers can come out of the expectation. So we can just move them out of it. So what's left inside the middle term is ex. And we still have e of mu square. Does that make sense? And now it's funny because, hey, look at that, e of x. We just mentioned e of x is just mu itself, right? The mean. So therefore, that's also mu. So therefore, what we have here is e of x squared here minus 2 times mu plus e of mu square. Wait a second, e of mu square. Mu square is just a constant because mu is a constant. Mu is just 1.5. So it's, do you guys see that? So really, so that's another mu square basically. Hey, so that's pretty much it, right? So, oops, sorry for that. Oh, how do I keep doing that? Oh, okay. All right, there we go. And finally, so what we got is e of x squared and minus 2 mu square plus mu square is just minus mu square. So sometimes we just leave it like this. So this is the variance, var, the variance of x, like that. Or maybe I can do it again, a better job. There you go. But sometimes, because mu itself is e of x, we can sometimes we just express it like this, minus e of x square. Notice that the square here is just inside the expectation versus the square here is outside of it. And that's it. So based on this formula, let's just go ahead and recalculate the variance. Earlier we got the variance as 0.75. Let's see if in our second attempt we can get the same thing. So all we need is the expected value of x squared itself. Now x was 0, 1, 2, 3, right? So therefore the squares will be 0 square, 1 square, 2 square, 3 square, and with the same probabilities. So basically we will rewrite this, except that we will rewrite them with squares. All right, so e of x squared, so for the first part basically. So with 1/8 chance, we will get 0 square. With 3/8 chance, it will end up being 1 square. With 3/8 chance, 2 square. And with 1/8 chance, 3 square. Minus. Hey, the last term was e of x is just mu square, but mu was just 1.5, so we are just gonna square it. That's pretty much it. So we can just factor out the 1/8. So what's left here is, well, actually this one is totally gone. So 3 plus 3 times 2 square, which is 12, plus 3 square, which is 9, and minus 2.25. And indeed this is 3 plus 12, 15 plus 9, 24. 24 with 8 is 3. 3 minus 2.25. That just ends up being 0.75, which is exactly the same answer. So now you learn 2 different ways to calculate the variance as well. Now I want to finish with an example, and hopefully we can just combine all this story. The example is the following. Consider, so in the previous example, before I go to that next example, notice that we came up with this by using some counting and stuff like that. So we derived the random variable. Most of the time this random variable is given to us with the probabilities right away. We don't have to derive it like we did last week, step by step. If it's given right away, we can directly do the calculations. All right, so here is our new random variable. This time let's call it say for instance y. So y can take different values. Let's call the values that it can take as lowercase y. And it turns out that it can take one of the following values. It can take either 1, 2, 3, or 4, one of these 4 values. And each one happens with the following probability, y equals y. So it becomes 1 with probability 0.4, 2 with probability 0.3, and so on, 0.2 and 0.1. Those are the given probabilities. So given these probabilities, let's calculate the expectation, the expected value of this random variable y, which is pretty straightforward. So it will be taking the value of 1 with probability 0.4. So 0.4 probability, you will get the value 1. 0.3 probability, you will get the value 2. Plus, let's continue from here. With a probability 0.2, we will get the value of 3. And with probability 0.1, we will get the value of 4. So if we were to add them, so 0.4 plus 0.6 is a 1, plus 0.6 is 1.6, plus 0.4 is 2. It turns out to be a pretty even number, so 2.0. And next we can calculate, for example, the expected value of, how about this? How about the expected value of 1 over y? How about the value 1 over y? Well, it's an expectation after all, which means we will continue to use these probabilities. All we need is, instead of using y, the values 1, 2, 3, 4, now we will use the reciprocals, 1 over 1, 1 over 2, 1 over 3, 1 over 4. So the probability is 0.4, that 1 over y will be 1 over 1. With probability 0.3, it will get the value 1/2. With probability 0.2, it will get the value 1/3. And with probability 0.1, it will get the value 1 over 4, because we are calculating the expected value of 1 over y. All right, so that will give us 0. How can I do it? We can either find the common denominator, or we can directly calculate them, I guess. So 0.4 times 1 is 0.4, plus 0.3 times 1/2, or half of 0.3 is 0.15. 0.2, a third of it is 0.067, something like that, I guess, if I'm not mistaken. And the last one, plus a fourth of this one, 0.025. There you go. So if we were to add up all these numbers, that will give us the value for the expected value of 1 over y. Let's just go ahead and let's calculate it up to 4 decimal places, because even this one was just an approximation, right? So I was kind of lazy. Maybe we should do a direct calculation. Hold on. Let's just find the fractions in terms of fractions. All right, so 0.4 is just 4 over 10. Let's just write them like that. Plus, the next one is 3 over 10 times 1/2, so it's 3 over 20. Plus, the following one is 2 over 10 times 1/3 is 2 over 30. And last one is 1 over 10 times 1 over 4 is 1 over 40. Are there any simplifications? Okay, let's not worry about that. Let's directly find the common denominator. I believe it will be at 120. So at 120 common denominator, I need to expand the first fraction by 12. So that would be 12 times 4 is 48. Plus the second one will be multiplied by 6. So 3 times 6 is 18. The next one is 4. So 2 times 4 is 8. And the last one is by 3. All divided by 120. So 48 plus 18 is 66. Plus 8 is 74, plus 377 over 120. Okay, hold on. Let's make sure we didn't mess up. So 48 plus 18, 68, 66, 76, 74, 77. Yeah, I think it's correct. And that's pretty much it. At this step, we can even find an approximate answer to that. Let me use my calculator here. So we would get 77 divided by 120, so 0.64167. So the expected value of 1 over y, so that's a different random variable, 0.6417. There you go. And then, for instance, how about the expected value? Okay, so let's do a couple more examples. How about the expected value of, say, for instance, y squared minus 1? Well, the expected value of y squared minus 1, let me just put a line over here, would be, well, at first, we can either do it directly. It's just an expectation of this. Okay, let's just do it directly, I guess. Well, the probabilities are still the same. So 0.4 times. So we need to square the individual y's and then subtract 1. So 1 squared minus 1, so that would be a 0. Plus 0.3, 2 squared minus 1, that's a 3. Plus, let's continue here. Let's put another line over here. 0.2 times 3 squared minus 1, that's an 8. Plus, and the last one, 0.1 times 4 squared minus 1, that would be a 15. That's pretty much it. So this one is gone, 0.9 plus 1.6 plus 1.5, if I'm not mistaken, and this adds up to 2.5 plus 1.5, that's a 4, an even number. All right, actually you could have noticed this alternatively using the following trick. Let me just show you. Until you get kind of proficient with all this, it will take a while to use the expectation operator, but it's a very useful one in statistics, mathematical statistics actually. So because expectation is a linear operator, it will distribute like we did earlier. So the expected value of y squared minus the expected value of 1. Wait, 1 is a certain number. There's no need for an expectation. It's just a 1. So therefore, all we need is the expected value of y squared. So we can do it the same thing, except with a y squared. So the first number was 1 squared. Plus 0.3 times the second number was a 2 square, huh? Remember? So that's a 2, and then 3 square, and then 4 square. Plus 0.2 times 3 square, plus 0.1, oops, 0. 4 square. There you go. So we have 0.4 plus 4 times 1.2 plus 9 times 1.8 plus 16, so this one is 1.6, and long behold, if we added these numbers, hopefully we should get a 4, right? So 1.2 plus 1.8 is a 3. Wait a second, that's a 5. Oh yeah, that's a, oh, I totally forgot about this one, right? So minus 1. I totally forgot that, minus 1. So we got 5 for the first part, minus 1. So that will give us 4. Yes, and look at that. That's the same answer as the previous one. So there's you can be creative and you can find alternative ways to calculate the same numbers. Lastly, I think we just did the expected value. And then I got distracted and I showed you all these, the expectation of something else and something else. Why don't we also, again, directly calculate the variance? So the variance is, again, like we did earlier, it's a different type of expectation. Again, so expected value of this number. So that's our variance, right? So, but why don't we use the definition, oh, sorry, not y, x, y, the random variable right now is y. So why don't we use the alternative definition that I showed you? How about this one? Minus e of y square. Now why do I especially want this one? Because I already calculated e of y square earlier here. E of y square, I just found out that it was the sum of these 4 numbers, which was just 5, minus, and e of y itself came out as 2. So that one came out as 2, and then I need to square it further, and that's it. 5 minus 4, that's a 1, and that is the variance of this random variable y. All right, so hopefully this was useful. So in the so we went over 2 examples. So that was our second example. Maybe I can just write it here. So this is example 2. In the first example, we went through the discrete random variable that we looked at last week. This is a binomial random variable, as you can remember, and we rolled the die three dice, and we counted the number of heads. We derived these individual probabilities last week. You can go check to the material from last week. I don't want to go and do that again, but instead what I want to focus here is the expectation operator, and using that operator we were able to calculate the expected value, this one, and the variance, that one. But then later on I realized that expected value and variance are just two of the many statistics. So why just focus on just e of x or e of this number? We can do e of anything we want, right? So basically, as long as you know how to use the expectation operator, for instance, we learned an alternative way to calculate the variance, which turns out we after our calculations we found out it's this. So that's why we, on the second example, what we did is starting with this random variable, I didn't even define it. Do you guys see that? I don't care what is the interpretation, as long as someone gives me the values that y can take and the respective probabilities. After all, it's a random variable, right? So it's a random variable, so its values that it can take has some underlying probabilities, right? So 4 values that it can take with these given probabilities. So given that, so we were kind of we looked at different expectations. So what would be the expected value of y itself, given that it can take the values of 1, 2, 3, or 4 in average? What will be the value? It turns out that because 0.4, there's more weight to 1, that's why the average turned out to be closer to 1, so which is 2 basically, rather than 3. It came out as a 2. And then later on I looked at the expected value. How about if in average y will be 2, in average what will be the value of 1 over y? And it came out like this. And then in average what will be the value of this one? And so on, right? So we were able to derive. And finally, in average, what will be the value of this expression? And this expression turns out to be the variance, so it has a special meaning. Among all the statistics, arguably those two, the expected value and the standard deviation, are the most important statistics. But there are many you can construct on your own. And so depending on the situation that you have, one might be more important than the other. But in most of the cases, the expected value and the standard deviation or the variance are the most important ones, turns out. All right, so hope to see you guys in our next lecture.